All right, hey everybody, welcome to AP Chemistry. Welcome to another live stream. So today we're going to be talking about the separation of mixtures and separation of solutions, which we'll later learn they are a type of mixture. So yeah, we're going to be talking about the separation of solutions and mixture chromatography. So I'm going to go to the slides right now. And we're going to start. So hold on. To figure out this thing. Okay, so we're going to move on to the next slide. So if you haven't been following our social media accounts, be sure to follow Think Flammable on our Instagram, Twitter, and YouTube, because we will be posting updates to our live streams, and you want to make sure that you are following it to stay up to date. All right, so today we're going to go over chromatography and distillation. Those are two types of ways to separate mixtures. And these are also two very common techniques that you're going to use in the lab. And you know, when you're in the lab, when you're separating mixtures, chromatography and distillation are two of the most common ways to separate mixtures. So you want to be familiar with them. All right, so, and then we're going to go over some molarity review to kind of get you familiar or get you more comfortable with converting moles and volume into molarity. All right, so if you can hear me, actually, like, can you please put in the chat box how you're feeling today? So are you feeling good? Are you feeling so-so? Put an emoji. Or also like just how you're feeling about AP chemistry too, because hold on, my screen is going whack. Yeah, so today we're going to go over some lab techniques, which is chromatography and distillation. Sorry, my slides are just popping all over the place. Okay, I'm going to minimize it a bit. Okay. Hold on, I'm going to minimize it a little bit more. Sorry about this. All right. I'm gonna move on to the next slide. So we're gonna go and talk about chromatography. Wait, hold on. Wait, actually, we're gonna talk about distillation first. Sorry about that. We're gonna talk about distillation. So for distillation, wait, hold on. Sorry, my slides are going whack. Hope this is better. Okay. I'm gonna minimize it a little bit more. Sorry about that. All right, so in distillation, we have a container of the solution that we want to separate, right? And then we have a heater on the bottom. So what we're trying to do is we're trying to figure out which component of the mixture is going to evaporate first. So in distillation, we're trying to separate the components in liquid mixtures, right? So the most volatile component will evaporate first. So yeah, so when we're doing distillation, I'm trying to figure out which component of this mixture or solution is going to evaporate the easiest. So which part, because as we're heating it up from room temperature usually, right? So as we increase the temperature, like 1 kelvins by 1 kelvins, you'll see like the one that evaporates first is the one that evaporates at the lowest temperature. So yeah, so we're basically trying to find out which liquid evaporates at the very lowest temperature. Here I have a pointer right now. And that liquid or that component of the mixture is called the distillate. So the distillate is the part that evaporates first. And what happens is as it evaporates, it moves up the tube, and then it condenses as it goes up. So there's actually a cooling tube. That's what they call it, a cooling tube, where the gas condenses into liquid again, and then it will move down this other tube and drip into another like container that you have on the side. So and so that way you'll have the liquid of the component that evaporated the easiest, and the rest of the other type of mixture or other components left in the original container. So basically what we're trying to compare here is the boiling point. So do you guys know what the boiling point is of a solution? Do you know like how, like if you were to explain it to me, how would you put it in your own words? Okay, so I think I see a question. Hi, this is not content related, but I was wondering if you could post these slides. Yes, I will post these slides. I will link it to, hold on, I'm going to put it in a call to action. Slides, URL. Okay, do you want me to post it right now, or would it be okay to like post it afterwards, after the live stream? I'm gonna, I think I have to figure out like how to share this slides, how to share these slides. Because I'm currently in presenter view, so I think I'm gonna do this after the stream, but I will post these slides. All right, so yeah, so do you guys know what the boiling point is? Have you guys studied that yet? If you could just like explain like in very simple terms what the boiling point is in the chat box, that would be awesome. Okay, if not, I'm going to kind of, okay, sorry, my slides are not cooperating today. The point at which the liquid changes from liquid to gas. Yes, that is right. So it's like, so yeah, so when you talk about the points, you're talking about like the lowest temperature, right? So yeah, the temperature at which the liquid changes from liquid to gas. Okay. So I'm on to the next slide. So this is kind of like a practice problem, all right? So so pretend we're going to run a distillation lab experiment, and we have two types of components in this mixture, in this solution, all right? So let's pretend that the solution in this container is made up of two types of mixtures, or two types of compounds. So there's the X compound and there's the S compound. So X boiling point is 320 kelvins, and S is boiling point is 360 kelvins. So which one do you think will evaporate first? So these are its boiling points. So that means like these are the temperatures at which the component or the compound is going to evaporate. So like if we had X and S combined in a mixture, not chemically bonded, but they're mixed together in a mixture over here. And if we were to heat it, which one do you think will evaporate first? So you could write down X or S in the chat box. Right, X, because X has the lowest boiling point, so it's like the easiest one to evaporate. So yeah, so like usually what we'll do in labs is once we get to like its boiling point, once we see a compound start to evaporate, we will kind of like stop the heating process. We will not try to let the solution cool down, but we'll try to keep it at the same heat. That way we don't like keep heating it up. Because imagine if we were to heat past 320, and if we were to heat into like 360, then both of the components will be evaporating. Then that will not be what we're trying to do. So we're trying to stop at kind of like the temperature at which like the first the first component boiling point is, so that we can kind of separate those two components, those two compounds. So yeah, the compound with the lowest boiling point will evaporate first. Yeah, and so that's kind of what I just said. you will stop at a certain temperature until X has all of X has evaporated and condensed. So over here we have a little animation or a little picture of what it actually looks like. So you see here we have like a heating device, and we also have a thermometer up there to keep the temperature in check. And then as the component, or the one with the lowest boiling point, it moves up this tube, and into this tube it will start cooling. And then once it starts cooling, it starts turning from a gas into a liquid, and then it will collect in another container that we have on the side. That way we'll have like pure compound in one, and the other pure compound in the other, left in the other container. So now we're going to talk about chromatography. So in chromatography, we're trying to compare the intermolecular forces of different liquids. So have you guys covered chromatography yet, or have you done that in the lab yet? It's really fun. So what you do is you have a piece of paper. It's called chromatography paper, and what we do is we put dots of different samples on the bottom. So as you can see here, there's like a star line, right? So these different colored dots, they represent different mixtures. All right, so what we're trying to do here is we're trying to compare the polarity, or the intermolecular forces of these different mixtures. So so basically we'll put it into a solvent, which you can see over here. It's sometimes water, it's sometimes another type of solution. It could be iodine. And what will happen is the solvent will start like moving up the paper, right? So if you've ever like dipped a piece of even just regular paper into water, you can see that like the water slowly moves up the paper. So that's kind of what's going on here. The solvent's moving up the paper, and as it moves up, you know, if you've ever had ink on paper, you can see that the ink kind of goes with the water, right? Or it doesn't. Or I mean, I guess the pencil marks sometimes goes with the water, actually ink doesn't go with water because it's oil based. But if you have like a marker, right? If you have a permanent marker or a washable marker, then the color is going to move with the water. So like if you were to have a dot of like marker, like if you were to have a marker mark over here, like washable marker, then like as the water goes up, the marker ink is going to go up with the water. But like if we were to have something else that's not as attracted to the water, then it's not going to move up with the water as fast. So this is kind of the starting line. And so what we're trying to do is we're going to put this paper into the solvent, and then after a few minutes, we're going to go observe like how far the different mixtures have gone up the paper. So our chromatography basically compares mixtures based on their attractions to solids and liquids. The paper is going to be the solid here. So it's going to act like a wick, you know, to draw up the solvent, and the solvent will be the liquid. And the paper, hold on. So, right, so normally the paper is the polar object, right? And the solvent is a non-polar object. I'm going to move back to my previous slide. So mixtures with stronger attractions to the paper will cling up to the paper, right? So they will not cling up to the water, and so they will travel slower because they're kind of like trying to stay on the paper there. And those with weaker attractions to the paper will travel faster because they have stronger attractions to the solvent. All right, so normally, this was actually in a previous FRQ on the AP exam. I believe it was from the 2017 AP exam FRQ, and they had a chromatography experiment set up on the FRQ, and they asked the student to identify like which ink or which mixture, which like how would you call it, which mixture is the most polar or which mixture is the most non-polar, based off of the chromatography lab results. So so I'm going to kind of like go through like how you can decipher a chromatography lab result. So the fastest dye, aka the most non-polar dye, which I guess, yeah, all these mixtures, we're just going to call them dyes, okay, because they're different colors, so we're just going to label them as such. The fastest dye, or the most non-polar dye, will be most attracted to the non-polar solvent. So have you heard of the phrase like attracts like in AP chemistry? I know that my teacher kind of reinforced that in our heads. You know, like attracts like. So polar things are going to attract polar things. Non-polar things are going to be more attracted to non-polar things. If you've learned about intermolecular forces like London dispersion forces, you know that like you know, polar things are not going to be attracted to something that's like not polar at all. However, non-polar things, they can kind of induce polar charges, or I guess they can induce a dipole moment. I think that's how we would call it. They will induce a dipole moment, which means it will kind of force each other into a very slight polar state. So yeah, so remember the phrase like attracts like. So over here you can see if the dye is very nonpolar, then it's going to stick on to the solvent, which is nonpolar, as you can see over here. So it's going to be more attracted to the solvent. However, if the dye is polar, then it's going to attract on to the paper. So it's going to try to stay with the paper. So if you can see here, so as the solvent goes up, right? So let's say after 10 seconds, the solvent goes up, and let's say the solvent is up at this level. So you can see me draw a line here, drawing a line over here. Then you can see that this dye is like the one that's clinging onto the solvent the most. So it's traveling up with the solvent, right? But the dye over here is like the second most clingy one to the solvent. You can see the dye over here, that's the slowest dye. This is the one that is like the most reluctant to cling onto the solvent, which means it's more attracted to the paper. So it doesn't really want to move with the solvent. It wants to stay with the paper. All right, so the fastest dye, which is this purple one right here, it follows the solvent up the paper and is least attracted by the polar paper. And the slowest dye, which is the most polar dye, is right here. It is the most attracted to the polar paper. All right, I'm gonna move on. All right, so now we're going to go over a little molarity review. So do you guys have any questions before I move on to molarity? Do you have any questions on chromatography? Oh, is the solvent water? So yeah, so that's a very good question. So yes, the solvent, most of the time it is water. Sometimes it could be something else. It could be iodine. It could be, I know I did an experiment with using iodine as a solvent. But yeah, water, like if you were to use water, most likely it will be distilled water, right? Remember, distilled water is like the pure water where it's non-polar. So it doesn't have like any like other components or other minerals in there that will have, you know, that will have different dipoles or have another like polar moment. Yeah, and pure distilled water will also have a pH of 7, which is neutral, which means it's not like it's not a strong base, it's not a strong acid, or it's not even a like slight acid or a slight base, right? It's pure neutral. Yeah, so that's kind of why we use distilled water instead of like regular tap water. Do you guys have any more questions on chromatography or distillation? I'm going to check the question box. My slide is kind of blocking the way, so I can't really see everything. All right, I don't think you have any questions for now, so I'm going to move on to molarity. So have you guys gone over molarity yet? I think a lot of teachers, they go over AP Chem like chapters in different order, so it's kind of like a lot of people are like all over the place. They're like, some people have already done like electro batteries. Some other people have done chem equilibrium. But yeah, today we're going to go over molarity, and molarity is equivalent to concentration, right? So the definition for molarity is the moles of solute over liters. So they're over the 1 liter. So when we're talking about molarity, we're basically talking about concentration. It's the same thing, except we're using moles as the unit, right? So distilled. So we're going to do a practice problem right now. We're talking about distilled white vinegar. So distilled white vinegar is a solution of acetic acid, and it is in water. Okay, so a 0.700, mind the significant digits, liters of vinegar solution contains 10.2 grams of acetic acid. What is the concentration of the acetic acid in units of molarity? So do you guys know what the first step is in this question? So remember that the molarity equation, it is equal to the moles of solute, which the solute is kind of like the thing that we're trying to find the molarity for, right? So if we're talking about water, then we'll be using like the moles of water. If we're talking about white vinegar, we'll be using the moles of white vinegar. So yes, convert grams to moles. So hold on, let me see if I have. Yeah, so we're gonna first circle like the volume, and also gonna circle like the grams, right? The grams of acetic acid. So right, the first step is we're going to convert the mass into moles. And 1 mole of acetic acid, I'm not going to read this chemical formula, it is equal to, I did a calculation for you guys, is equal to 60.052 grams. Do you guys have any questions on how to convert this, or are you all good? Or no, never mind, I didn't convert it yet. This is the unit conversion. Sorry about that. This is the unit conversion. So what you do is you add up all the different like molar masses of these different elements, and then you have this 60.052 grams per moles. So so then next you multiply. So you put 1 mole over 60.052 grams, which is like the unit of 1 mole of acetic acid, and you multiply that by 10.2 grams of acetic acid, which is what we have right here. And that will equal to 0.170 moles of acetic acid. All right, and then we're going to divide the moles by volume, right? So the volume here is liters. So we can see here that the total volume is 0.700 liters. And mind you here that like 0.700 liters, it's not like the volume of acetic acid, right? It's not pure acetic acid. This is 0.700 liters of vinegar solution. And if you can see here, the vinegar solution, is composed of acetic acid and water. So over here, so we're dividing that by volumes, right? So So we know that it's not pure, like 0.700 liters is not pure acetic acid. It's a combination of acetic acid and water. But over here, we're just, for molarity, we're just trying to find, how many moles of acetic acid is in this solution, right? That's the big question we're trying to find, or trying to find the answer to. So 0. So we're going to divide the moles, so the amount of acetic acid we have, by the volume, which is 0.700 liters, and that will equal to 0.243 moles, or molarity. And we use a capital M to indicate molarity and to separate that from moles, or from mass. Or usually we don't use mass. So if we were to use mass, we would use grams, right, or kilograms, but we usually use grams. All right, so now we're going to do another practice problem, and this is on like concentration and volume. So this is in a case where we're not adding another solution to the current solution. So let's say that we have this concentration right here, so wait, hold on. Right, so what we're trying to find here is we're not adding like another, like, let's say we're not adding an HF, right, or another type of acid to this. So we're going to find like what volume of 0.15 moles of hydrochloric acid can be prepared from 15 milliliters, or this many liters, of 0.45 moles molarity of hydrochloric acid. So you can see here, we're not trying to add like another type of acid or another type of base. So then we know that we can use this problem. This is a very a problem that you really want to familiarize yourself with for the AP exam, because this is a very, very easy way to convert, to find out like how much volume do I have, so let's say we were to start off with like this many liters of this many concentration of hydrochloric acid, right? If we were to plug those in for the initial condition, and if we wanted a different mole, or a different molarity of this of hydrochloric acid of the same acid or the same solution, but we want to find out what would the mole be, or sorry, excuse me, what would the volume be for that? Then we would use this equation, and it's very easy, right? It's also saves you a lot of time, which is crucial for the AP exam, because you want to be able to find solutions very fast. Speed is very integral on the AP exam. So first we're going to circle 0.15 moles. We want to circle up like all the important units, all the things that we are going to use. Right, and we're going to circle up the volume and the other molarity, or the other concentration. So remember, C stands for concentration, V stands for volume. So now we're going to list out all the different values. So the concentration, so the one that we're going to start off with over here, or yeah, either way, you could either have these two values be the initial conditions, or these two values be the initial conditions. It really doesn't matter, because there's not really like it's not order sensitive, right? Because it's the same thing. So 0.45 molarity, I'm going to call it molarity, or concentration, times 0.015 liters, it's going to equal that. So we're going to plug those values in so that we can find that the final volume is 0.045 liters. All right, so that is the volume of 0.15 moles of hydrochloric acid that we can produce. And this is very useful, right? Again, this is very useful when you want to find, how much volume of this acid do I have at a different concentration. So like if we were to start off with this much, and I want to change the concentration, I want to find another concentration of this, but I still have the same amount of this acid molecule. I have the same amount of molecules, right? Then the volume has to change, because if you can see here, the concentration is smaller on this end, right? So if we have to make the concentration smaller, but keep the number of moles constant or the same, then we have to increase the volume so that, or increase the final volume so that the moles of hydrochloric acid is kept the same. So I hope that makes sense. Yeah, and also remember your sig figs, all right? 0.45. So we're talking about 0.45 molarity, or if we're talking about, like, we're dealing about, and this is essentially dealing with moles, right? So molarity, remember, it's moles over liters. So when we're dealing with moles or number of molecules, it doesn't really matter if we add like another 0 on the end over here, because like it's not very it's not so much like liters, like if we were to measure liters or if we were to measure grams, that would be different. But when we're talking about moles, when we are talking about amount of moles, then when we're talking about like 1 mole, you can usually assume that it's like 1.0 moles. Yeah, so like usually you can like it's okay if you add on another 0. So over here you can see that the liters, there's 1, 2, yeah, there's 1, 2, there's 2 significant digits. Am I right? I believe I'm right. Let me know if I'm wrong, by the way. I think I'm right. Yeah, I believe there's 2 significant digits. And yes, correct. Okay, thank you so much. I just had like a mind blank right there. So we're 2 significant digits. So if we were to have like 150 liters, right? Then we could usually add another 0 in the volume, because like these are all like mole quantities. This 0.5, it's moles, right? This 0.45 is also mole quantity. So usually that is fine. Okay, so okay, I think that's all that I have for today. So do you guys have any more questions for me? I'm happy to answer any questions you have. So what chapters are you guys currently learning in AP Chemistry? Like what subjects are you, or I guess what topic are you guys currently on? Because if you guys don't have any questions, I'm going to talk a little bit about intermolecular forces. I think that's always I think intermolecular forces is a really fun. Yeah, okay, that's awesome. Okay, so I was just about to discuss intermolecular forces. So I don't have the slides for it, but I'm going to kind of go over them. So do you guys know the 4 different types of intermolecular forces? Or maybe you could just like list a couple of like types of intermolecular forces that you know from the top of your head. So the ones that I have here, not all, but I think London dispersion, hydrogen bonding, dipole-dipole. Right, awesome. So yeah, I think you got like, yeah, you got basically all of them. So there's the London dispersion, there's dipole-dipole, there's ion-dipole, and there is hydrogen bonding. So I think today I'm going to focus a little bit on the hydrogen dispersion force and the the dipole-dipole, or actually the dipole-dipole and ion-dipole, we can do them both. We can also talk a bit about the hydrogen bond too. So yeah, so today I'll just go over all four of them. So do you guys know the difference? Oh, first of all, do you guys know the difference between intramolecular and intermolecular forces? Remember to mind the intra and the inter, right? Like those two are completely different forces. So is intermolecular forces between molecules? Yes, exactly. That's right. So intramolecular force is like if you were to have a water molecule, right? So the bonds between H and O, they're all intramolecular forces. However, so like when one water molecule, another water molecule, when they are close together and they start, they don't chemically react, but they kind of stick together, in some way, like it's a kind of a weak bond, then that is called an intermolecular force. Because, it's like two separate, two non-chemically reacted molecules coming together, kind of feeling attracted, but not chemically attracted. All right, so that is what intermolecular forces are. And intermolecular forces, they are the reason that we have solids and liquids, and they are the reasons that we have different phases of matter, right? We have the solids, we have, or they're the reason that, something would change from liquid to gas to solid. So if you've been here for my gas live stream, you know that gases, they reach an ideal state at high temperatures, right? So at high temperatures, they're moving super, super fast. However, if you were to lower the temperature to so low that the molecules are not moving fast at all anymore, like they're basically dead, right? They're basically like just kind of frozen. If you were to lower the temperature so low that they're not moving anymore, then you have a solid, right? You have a solid, and they're just vibrating. So, that's kind of the thing about intermolecular forces, where the temperature change can affect how closely the different molecules bond with each other. So for gases, those gas molecules, they do have intermolecular forces, so they do attract each other, but when they're at super, super high speeds, they're kind of, think of New York City, right? People aren't going to like stop and talk with each other, talk with strangers, because there's like a high, like everything is at high speed, and things aren't going to be super attracted to each other. However, at low speeds, that is when the different like molecules are going to start attracting each other a little bit, and as solids, that's when that's the highest intermolecular force, and that's when the molecules are essentially like the closest apart, and they're the most, they have time, to attract each other. So all right, so I'm going to talk about intermolecular attractions, and all right, so we're going to talk about London dispersion forces. So London dispersion forces, all molecules have London dispersion forces. So London dispersion forces, it increases with the surface area of the electron clouds around the atoms. All right, so if we were to have a molecule, right, that is, have you seen those, like, okay, so here, let me show you something. So in that previous problem, you can see here, like, distilled white acetic acid, right? It has a super, super long chemical chemical formula, right? So basically, the longer the formula is, that kind of means that the bigger the molecule will be, right? So if we were to draw out a Lewis diagram, then we will see that it's bigger than just an OH, right? It'll be bigger than like a hydrogen, like H2, right? A hydrogen gas molecule. So basically, the bigger the molecule is, so the more surface area the molecule is, the stronger the London dispersion force will be for that molecule. So it's kind of like the bigger the molecule is, the more chances there are for another for like London dispersion forces to happen, because London dispersion forces, they occur when two very similar molecules, they come together. So maybe they're equally nonpolar. So for London dispersion forces, like usually when we talk about London dispersion forces, we're talking about nonpolar and symmetrical molecules. Because for the other molecules that are polar and unsymmetrical, they usually already have like a polar dipole, right? They already have their dipoles and their charges going on. So they already have those like strong, like those strong, like I guess you could call it like a strong intermolecular force, or yeah, a strong intermolecular force. But when we're talking about when we're talking about London dispersion forces, we're usually talking about those molecules that are perfectly symmetrical, and you kind of think of them as the ones that don't attract anything else, because they don't really need to attract any other molecule, right? But they still do have intermolecular force, and that is the London dispersion force. So so what happens is, let's take hydrogen gas. So actually, let me try to see if I can find a picture of hydrogen gas. Hydrogen gas. So hydrogen gas, it's a perfectly symmetrical molecule. Have you guys gone over some like symmetrical shapes of different molecules? Like what kind of shapes would create a symmetrical hydrogen, or a symmetrical molecule? Have you guys gone over that yet? Like different shapes. I believe there's like planar. There's there's the different pyramid shapes. There's also the seesaw shape. I forgot what they're called. I can think of like the pictures in my head, but the images in my head. But yeah, you do want to memorize those, because those kind of show you like which molecules are going to be polar, which molecules are not going to be polar. So yeah, so the London dispersion force, it's going to be based on the size of the molecule. And a symmetrical molecule is only going to have London dispersion force as its only intermolecular force. All right, so okay. Anyways, I'm going to abbreviate London dispersion force. Let's just call it LDF. All right, so LDF. So if we were to look at helium, or actually never mind, we're not going to look at helium. So yeah, so like symmetrical molecules, they have low polarization, which means they don't have like the dipoles or anything. And so one thing about LDF is it's often considered the weakest intermolecular force. All right, so do you guys know what that means? The weakest intermolecular force. So if we're comparing, LDF against dipole-dipole or ion-dipole or hydrogen bonding, as you said, oftentimes you think, okay, London dispersion force, it's like the last resort. It's kind of like the one that's always there, the force that's always there, but it's not very strong. It's just like it's not very special, right? But like actually, in reality, they increase with molecular size, so they can eventually become greater than the most strongest dipole-dipole or even hydrogen bonding. So if you've already learned about intermolecular forces, you might know that hydrogen bonding is the strongest intermolecular force that there is. But at least, yeah, that is like, I know that like when I learned it, it was like the strongest. Like I would consider it the strongest. And so yeah, so So LDF, like if they're super, super big, if you're comparing to all these different type of molecules on their intermolecular forces, if you see like a molecule that is super, super long, right, that has a lot of surface area, then it has a huge huge LDF force. And so if you've seen those like long carbon chains where there's a lot of different carbons linked on each other and they have hydrogens coming off of them, they have a lot of surface area, which means that yeah, they have a lot of intermolecular force. All right, so now we're going to talk a bit about the dipole-dipole force. All right, so the dipole-dipole force, it's when we're talking about dipole-dipole, we're talking about attractive forces between polar molecules. So in this case, both molecules are polar, and with polar molecules, they're all unsymmetrical, right? All polar molecules are unsymmetrical. So these unsymmetrical molecules, they have like a permanent dipole-dipole attraction, right? They have like a permanent dipole, right? Essentially. So they're always going to have a a dipole-dipole force. All right, so if you guys have any questions, feel free to ask. I'm going to check my question box. I don't think I have any questions right now. If you have any questions about like a specific, intermolecular force, feel free to ask, and I can go into it a bit more. Oh, and one other thing about LDF that I didn't mention before is that like when we're on the AP Chem exam, and they're asking you to explain, why this one thing has a bigger, or this one molecule has a bigger LDF than the other molecule, right? Do not use molecular mass to explain, right? You have to talk about the surface area. So what you would say is like a larger electron's surface area is more polarizable, right, than another molecule that has a smaller surface area, or a smaller electron surface area. So yeah, so don't talk about mass. Don't say that, okay, this molecule has a lot of mass, so therefore it's going to have a greater LDF force, right? You do not want to use mass. You want to talk about the area, the surface area of the molecule. All right. So now we're going to go over ion-dipole forces. So this is when this is about the attractions of an ion to one of the dipoles of a polar molecule. So dipole. So like a polar molecule is like under the ion, right? So ion is like the one that it has like the strongest pole to another electron. The ion is kind of like the one that wants another electron the strongest. And when we're talking about polar molecules, they're like a gentler version of the ion, right? So they are kind of like temporary. They're maybe like half and half, right? They're half dipole, they're half one charge, they're half another charge, or they have more of a dipole moment, which dipole moments are more like this side of the molecule has like 75% of the time it's positive, or 75% of the time it's positive, whereas 25% of the time it's going to be negative. So dipoles, they are not permanent. They are more like, they're like they kind of vary with time. Like sometimes they're not one charge, sometimes they are. So water has a very strong dipole, right? So water's negative portion of the dipole. Hold on, sorry, I'm like trying to figure out something here. Right, so when we have like another ionic substance, per se. Let's say we have NaCl. Right? NaCl, if you separate it in water, if you dissolve NaCl in water, right, we're going to have the Na ion and the Cl ion. So let's just take a look. Let's just pretend the Cl ion, like or Cl ion is negative, so it's going to attract, like, it's going to attract the water to come close to it, right? So the water, it has dipoles. It doesn't have ions, right? The H's on its ends are not are not ions. They are dipoles. So I wish I had like the pictures to show you guys, but so yeah. So basically, like the Cl, it is the ion, and it's going to attract to the water's positive ends. So the positive ends are the hydrogens. So the negative ion is going to attract the positive dipoles of the water. So that is like one very simple example of the ion-dipole intermolecular force. And this kind of like water and other like other ion kind of interaction, this is very, very common on the AP exam. You want to be familiar with it. So whenever you see like one ion with like a lot of water surrounding it, a lot of water molecules surrounding it, you want to see, you like instantly know. Most of the time they're trying to ask you about like the dipoles, like how, like which, like is the positive dipole of the water attracted to this ion, or is it the negative dipole of the water attracted to this ion? And you want to kind of, and they might also ask you like what, like why is the water attracted to the ion? You know, is it because of is it because they're chemically reacted? Which you would answer no, because this is intermolecular force, right? They're not chemically reacting, they're just attracted to each other. All right, so now we're going to talk about the hydrogen bond. So this is a very special type of dipole-dipole interaction between a intensely positive charged hydrogen atom and another polar molecule's negative charge. So when we're talking about hydrogen bond is always a hydrogen bonded with another element or another part of another molecule. So so when we're talking about hydrogen bond, we're talking about the hydrogen being bonded to either a nitrogen or a oxygen or a fluorine. Fluorine. So they're not pure, right? So like so the N could be part of another molecule, right? It's not going to be floating by itself. The O is not going to be floating by itself. The F is not going to be floating by itself. It's all connected to something else. However, the H is going to kind of like, so the hydrogen, so basically what happens is there are two different molecules. One molecule has either an N, an O, or an F. And another molecule has H's. You know, it has lots of hydrogen on its outside. And the hydrogens, they're going to see, oh, there's an N, or there's an O, or there's an F. Then it's going to come close and it's going to attract the N or the O or the F. So that's basically how hydrogen bonds work, and they are super, super strong. They're considered the strongest among the intermolecular forces. All right, so I think that's all I have for today. If you guys have any questions, sorry to interrupt you, but can you have, yes, don't worry about interrupting me. Like, feel free to ask questions. I love answering questions. Sorry to interrupt, but can you have polar, wait, hold on, I'm going to, okay, so sorry to, can you have polar and non-polar ionic bonds? I know you can have polar and non-polar covalent. So do you mean like can they attract each other? Like can they have intermolecular force, intermolecular attractions with each other? Is that what you mean? Oh wait, hold on. Wait, never mind. So you're talking about ionic bonds. So yeah, so for ionic bonds, no, you cannot have nonpolar ionic bonds. For ionic bonds, they're always polar. And that is because, so let's take NaCl, for example, right? NaCl is like a classic example. So Na is the positive side of the ionic bond, and Cl is the negative side. So, there's no way that they can, like, they share they share it equally, because they have way different electromagnetic forces, which if you look at the periodic table, you can see that like one side is going to like is going to how do I explain this? There's like so do you know like what I think it's electronegativity is? I can give you, okay, so I have another like set of slides that have like super useful information um on like electronegativity. So like it goes over how size matters, right? How size of the atoms matter and how they contribute to electronegativity. Because I can give you those slides and they're very easy to understand, because like you can see it visually. You can see like how the molecule's size, decreases as they go from left to right of the periodic table. And you can see how, in that way you can see like how the strength of the different atoms kind of compete against each other to take each other's electrons. So yeah, so you cannot have nonpolar ionic bonds, because ionic bonds are kind of defined as, there's these two different types of elements or atoms that have very dissimilar dissimilar sharing forces. So the way I like to think of ionic bonds is that like they're kind of the same thing as covalent bonds. They're all sharing electrons, right? Except for ionic bonds, the different atoms, they have such different strengths with each other. That like let's say I have a little brother here, right? And if we were to share something, and if I, as a bigger sister, if I wanted the thing more than my little brother, I'm going to have greater strength, so I'm going to take it. So like we're kind of sharing, but we're sharing very unfairly. That's how I like to think of ionic bonds. So ionic bonds, yeah, they're sharing, but they're sharing like so unfairly that like one atom, one side of this sharing agreement is having way more of an advantage than the other side. So I hope that makes sense. So, so when we're defining polar and covalent bonds, the middle, there's like this middle fuzzy ground, right? Where, where both people, they do not have equal strength. So they don't share 100% fairly, but they're also not like 100% of the time, just like 100% of the time, like keeping the thing to themselves, right? Or like one side is keeping it like to themselves. So yeah, so like there's still that like middle ground where it's like where people start to debate like, oh, is this ionic or is this covalent, right? Is this an ionic bond or is this covalent bond? Yeah, so for covalent bonds, yeah, so like when we're talking about like that fuzzy middle ground where we don't really know if it's ionic or if it's covalent, that is usually when the covalent bond is polar, right? That is when there is kind of like an unfair sharing going on, and that is why it's polar covalent, right? But if the two molecules, let's say it's hydrogen gas, right? Both atoms are all hydrogen, so they're equal, they're the same. Then when they share, it's 100% fair, right? Like they both have equal strength. They're taking, yeah, they both have equal strength. So so that way there's a nonpolar covalent because they're sharing and neither side is more positive, neither side is more negative. They're like they have equal time they share their electrons equally. Right? I hope that makes sense. If that doesn't make sense, let me know and I can clarify a bit more. Does that make sense? Okay, awesome. So if you want the slides, yeah, I'm going to post the slides actually right now so that you can see them. Hold on. Would you like the slides to the one that I just described, or the hold on. Would you like the slides to my other stream that like explain the electronegativity, sizes, and all that? Yes, please. Okay, awesome. I'm gonna go and find that for you. Hold on. So do you have any more questions as of now? I'm gonna post it in the chat, I believe, if that is okay. Hold on, I have to figure out how to share my slides right now. I have to go on at like the advanced settings and change the settings of my slides. But do you guys have any more questions? How are you feeling about AP Chem right now? Are you feeling good about it, or a little bit uncertain about certain? Okay, awesome. Yeah, that's like not great. Like, so what subject are you like the most shaky on? I know that like for me, a lot like I think last year there were some subjects. I think it was the acid base subject or topic that really threw me off. And it was just really hard. Come on. Shapes probably. Oh yeah, shapes. Yeah, shapes. Honestly, like for the chapter test, I kind of crammed and yeah. But I know that like as times go on, like I don't think you have to like remember shapes for all different chapters of AP chemistry. So that's a good thing, because like when we are going over like titrations or acid-base equilibrium, like those other topics, they honestly don't take shapes into account as much. I think shapes really do come in play when we're talking about intermolecular forces, right? And polar, nonpolar, all that. So yeah. All right. So if you guys don't have any more questions, that is the end of my live stream. So I'm going to post the slides on right now. I hope that you can access them. I'm going to post the first one right here. Yeah, I'm going to, so do you guys have any more questions? I'm going to end the stream right here. I'm going to still like, if the link is not working, just let me know in the chat and I will try to fix it. I'm going to find my other set of slides right now. I'm going to post it. Okay, awesome. So I'm going to find my other slide and post it. But yeah, so I see that there's no more questions. So again, thank you guys for coming to this live stream. I hope that you guys have a great rest of your day and a great rest of your week. And keep persevering in AP Chemistry. You can do this, okay? It's going to get fun. I know there's a lot, like, I love AP Chemistry. There's a lot more fun chapters coming up. The shapes are not the most fun to deal with, but there are other topics that are going to be a lot more fun. So hang in there. You got it. All right. So have a great rest of your day. And I will see you guys next time. Bye.